Well, I hope you're going to enjoy your day. What I want to say is very simple, but parallel processing is very simple and should be very simple. And the trouble is that everything always gets much too complicated. Well, there's a question, the future. Does it have a future? It's the future in the past. What is going to happen? Hopefully, there will be lots of it. What I want to talk about is more cores on a chip, where we are today. I'm afraid I'm going to bore you with Iann Barron's Transputer, but it was simple, and you must remember it. And then we can speculate about the future. In 1963, Gillette introduced the disposable razor blade. Plastic and metal stuck together, simple processing. It wasn't until 1971 that Intel came along with the microprocessor. And Gillette immediately responded by producing the Transputer. 2 blades, double the processing. Wow. And in 1988, they went one better. 3 processors. What was Intel doing? Just making its processor more complicated. It wasn't until 2005 that Intel actually got the idea to put 2 cores on a chip. And then, really encouraged by that, it put 4 cores on a chip. And that's about where they are today. But, of course, Gillette wasn't taking that line down, and they immediately came back with 5. And where are we going in the future? Well, there's been speculation that Wilkinson and Ship will come in 2015. And what would Intel do? Where are we? What actually happens? How much parallel processing is there? Whoops, why did that go away? Yes, the one place where we get parallel processing, of course, is the operating system. Programmers and computer scientists can't cope with parallelism, so they hide it behind this wall. And there is parallel processing going on in all your computers behind the operating system. And of course, it doesn't work very well. But we have another example of parallel processing, the internet. And there we have a huge community of computers all working happily together. Really very successfully. Now, what's the difference between the incompetent operating system made by Microsoft and the internet? I suggest to you simply that in the internet, the concentration has been on the communication process, on making that secure and controlled and safe in such a way that nobody can bugger it up. Go back to Microsoft. What have they done? They put down 60 million words of code. They put in an insecure operating system in which people would still get blue screens, a little label saying buffer overflow, buffer underflow. It happens all the time. Usually it isn't actually Microsoft's fault, because what's happening is that the problem is that some bit of third-party software has interacted with the operating system, probably with another bit of third-party operating system, and the interface is insecure and it falls down. So I say it's not Microsoft's fault. Of course it's Microsoft's fault. Whoops. you jumped a bit, never mind. Because they provide the insecure interface. What we do get is, in terms of parallelism again, what's Intel done, it's made its microprocessor more and more complicated. It's put in super pipelining, try and exploit the parallelism that it can on the chip with the instructions. It's made them super scalar, so it tries to look for low-level parallelism in the program itself. And what do you get from it? Well, on a good day, you might get a 3x performance improvement. And most of that has come well, it doesn't come actually. That's what they think they get. And think of all the silicon they used up to achieve that. The other thing is, that, of course, they've actually introduced multi-cores. 2, 4, well, you get 4 mostly these days, and they give you 4 free ones as well as virtual processors. So they say they've got 8. What do you get out of that? Again, actually bugger all. Probably the average system sees about a 1.5% increase in performance. And how do you get that? Well, actually the operating system sitting in one processor and the other stuff sitting in another. So, not really very good use of silicon. And the other thing, of course, we've got to is massively parallel computers. We do have computers out there with large numbers of processors in there, heating up the atmosphere and producing some useful results. And the basic paradigm of these computers, on the whole, is that we've got lots of processors and they're addressing a common memory. And after that, it's up to the programmer to sort out all the issues and interactions. They may have some operating system support in doing this, and they may not. So they're very hard to program. But they're doing useful work. Current applications. I was going to ask you, what do you think the most important current applications are for parallel computing? Anybody got any ideas? There must be one somewhere. Yes.
Probably satellite TV and things of that nature, where there's lots of on-the-fly encoding.
Right. Any others? Yes.
Face recognition and security recognition of scanning certain objects and seeing the differences.
Okay.
Weather simulation?
Yeah.
Particle accelerators like CERN, when you need a lot of precision.
Yes, in total. All right. Well, I had to think about this. I came to the conclusion that I think the most important application is digital television. There is parallel processing going in every television set at the moment. It's usually done by ASICs rather than microprocessors, but it's there. And almost everybody has one. Oh. I'm sorry this is jumping, don't know why that is.
Use the keyword apology.
Yes, you're probably right. Alright. Let's try that. No. Well, we'll stay with that at the moment. You'll have to put up with the grey stuff. GUIs obviously use parallel processing. A little bit in the microprocessor, mostly in the graphical processing units. But lots of it. Is it doing any good? No, it's just a marketing tool, isn't it? So it's not really very worthwhile. Games, yeah. We do actually use parallel processing in games. Most of it is just simple ray tracing, but it's there. Biggie, yeah. That actually works. All the search engines are out there, wanging away in parallel, giving you results in small parts of a second. And we do some mathematics. It's mostly some form of computational fluid dynamics. It's usually a three-dimensional space with local interactions. Lots of examples. And the other one, mathematics we do, is Monte Carlo methods. Not really terribly impressive, is it? And if you think about those, they fall into some simple classes. The great one we can actually do is when the computations are all independent. Searching, Monte Carlo, you don't have any interactions between the processors. They all run in parallel and you get the result at the end. The second, you collapse it down into a two-dimensional space and you then can do your computations. And the nice thing about that, mostly you're only communicating very locally within a set of processors. Now what we don't do, and where the future is going to be, finite state interactions, where actually you've got a better program and it's got a lot of state with it and it interacts with a set of data and say it does it differently to the next processor. A sort of typical example of the thing you'd like to do, or you don't do very well at the moment, is simulating cars driving around on a road. They act intelligently, they interact, and we can't do that using current mathematics. So, my message, and it really is important, is I think that what we're going to see with truly massively parallel processing is a whole different class of applications. Things that people haven't even started to think about yet. Things where we haven't done the mathematics yet. And we all know parallel programming is hard. Been dinned into us for years. Why is it hard? Well, go back to the experience of InMOS 30 odd years ago. We found, quite surprisingly, that engineers were much better at parallel processing than were programmers. And just to put the symmetry into this system, we found that programmers were damn sight better than the engineers, these electronic engineers, at laying out printed circuit boards. Now, why? And there's a simple answer, and it's really very important. If I'm an electrical engineer, I'm trained to think about the things that are happening. I've got a circuit, all the bits are switching at the same time, and I have to cope with that problem. If I'm a programmer, I'm told you write a program sequentially, one step at a time. And that's the way it is. So there is an important teaching thing that we teach. Don't teach computer programmers how to think in parallel. And the converse is, as I said, why were computer programmers better at laying out printed circuit boards? The answer is it's a damn difficult thing to do. It's extremely complex. And that's what computer scientists are taught. They actually taught to manage complexity. Programs are incredibly complex things. So you've got to put those two things together to be able to program in parallel. As I said, we need to change the way we do computer science And it's also hard because we don't have any decent programming languages. What we do is we take the existing programming languages and we wrap something around them. And the last problem is that you bet mathematics is sequential. How do you think about a problem in mathematics? You think about it in steps. How do you write a proof? You write this line, then the next line, and then the next line. And most mathematical systems, the thinking is again pretty sequential. When Mr. Wiles proved the four-colour theorem, he used lemmas, and they were lemmas solved on a computer. And what were these lemmas? There were 50,000 of them, and they were parallel step in the proof. And they were the crucial step, of course. And what was clever about what he did was that he later proved there were only 50,000 parallel steps that were necessary. So I think we're going to see mathematics change as well. And as I said earlier on, we're probably trying to address the wrong problems. Parallel processing is going to enable us to do new things. Well, there are lots of parallel programming languages. I did a count. I've easily found over 100 quite well supported languages. That doesn't help, does it? And there are lots of languages. Erlang, Linda, Occam, Smalltalk. They're all different types. You remember Peter Landin, he talked about syntactic sugar, and he meant just part of the programming language, but really, you could apply that in this context, the whole of the conventional part of a sequential programming language. They sort of come in three main varieties. They can be imperative, they can be object-oriented, or they can be functional. Take your choice. To get to a parallel language, we have to add something, and what we have to add is some model of concurrency. And that's pretty much the way we get to parallel languages. People choose the syntactic sugar they want, and then they choose some model of concurrency. And so you can get 3 times or 4 times as many languages without any difficulty. What are the paradigms that we use for concurrency? Well, the great one that people have flogged their lives over for 30 years is we don't want to know about concurrency. Let the compiler solve the problem for us. And the results of this? A lot of hard work, no useful solutions. Why? Because the concurrency is in the way you view the problem. The amount of concurrency that's in an algorithm is there because you put it there. Current programming languages don't have concurrency, so compilers can't do very much about that. And all they can do is identify the very low instruction level parallelism, which dear old Intel's now doing for us on chip, so that's not a very good idea. Second model is, well, it's up to you guys. Here are the processors, there's the memory, sort it out for yourself. And most of the big parallel computers use shared memory. Paradigms, there are some languages that support that, like Linda, but most often either you don't get any support at all, and you have to use locks and things, or prayers. Or you allow the operating system to solve the problem for you. And as we know, operating systems are the things that get in the way of programs running. We do have a model, actors. What's an act? Well, Carl Hewitt was a wild sort of guy, if you remember him. All this stuff happened 30, 40 years ago, because nothing's happened since then. An actor's an object, which can communicate in parallel with anything else in the world. in any way you like. No synchronism. You can communicate with any name thing you want. Well, it's paradigm. It's pretty hairy and pretty difficult. Don't like it much, as you can gather. The other sort of thing you can do, which is where we went with the Transputer and Occam, is communicating sequential processing. And that's going to entirely the other end of the spectrum. It's trying to have an entirely formal, simple method of communication, which is quite restrictive, but if you're clever about it, you can actually prove your programs work, you can see things, and you can write programs. Still has difficulties. Now, I want to just say some things about Occam. So, Occam was there as an incredibly simple language. It had the minimum amount that was necessary to enable us to run a microprocessor. But that's a good starting point. It has to have some idea of a process the calculation extremely strongly. Occam. Everything happens inside a process. And there are actually two elements that when we talk about it. There are processes and there are communication channels. And that's all there is. The communication channel is an extremely simple object. It happens to have a procedural form, not really all that important. Processes encapsulated, you can send messages out of a process to another identified process, or you can input, and it's simply implemented in the language by in and out instructions. To create an object, a process which is itself contains internal concurrency, there's a construct, par, which allows you to declare that things are going to run in parallel. By symmetry, we also put in a construct to say that the process is going to run sequentially. Now, that's really a terribly good thing to do because we're trying to make the two things symmetrical with one another. Trying to get people to think that parallel and sequential are the same. They're not sequentially parallel is something you're going to do after you've done lots of sequential steps. They should have symmetry. And we found we needed something else just to remark. In any programming language you need a choice construct, usually an if of some sort. Turns out if you want parallel processes you need a choice construct on communications as well. So that's our ORC construct. And that's all you need to get to a parallel processing language. And we implemented this language in the Transputer. And the Transputer was specifically designed to run parallel processes. And it could support a set, it ran them, because it was a sequential processor, by time slicing between the parallel processes. So there was a set of instruction pointers which told you where all the processes were, and they were actually held in a list in the hardware, well, in memory supported by the hardware. And there are actually, it's not quite right, but it's the simplest way to explain it, two queues. One for the processes which were ready to run, and one for the processes which were waiting to run. And they were ordered queues so that you treated each time the process which had been waiting for longest. Just to make it even more complicated, there were actually two sets of priority queues, high priority and low priority. So there were processes ready to run and processes waiting, and they were waiting for a message from a channel. And process synchronization, we imagine process A was actually running in the Transputer. It would run a set of instructions until it got to communication. this is an input. Input and output are totally symmetrical. And it would then interrogate the channel, which is associated with the input. The channel was a location in memory, which held a pointer or, at a flag. And the channel could either be ready for communication or not ready. In the case that I've chosen, it's gone green and it's ready. So the processor A would transfer the message which was pointed to by the channel into its own memory space. It would reset the channel to passive state and then would continue on its way. And it would continue running until either it got blocked or it relinquished control on a time slicing basis. Now, that's one example. Now let's take the converse. We again have process A and it's running through a set of instructions until it gets to an input instruction. This time it interrogates the channel. The channel's not set, so it's blocked. It can't actually run anymore. It sets the channel into an active state, linking back to the processor A, and it then gets descheduled and waits for communication. Process B will run sometime later and run through a set of instructions until it gets to an output instruction. Again, it does a symmetric thing, it interrogates the channel, the channel's ready, it does a transfer of information to process A. Process A is now put on the active queue again because it can run, it's ready. Process B resets the channel and continues on its way. So we've done the communication process and it's done with the minimum amount of transfer of state and the minimum amount of swapping. Simple and cheap and easy to implement. And it was put on to what was actually a highly innovative machine at the time. It was the first 32-bit microprocessor. It ran 10 times as fast as its competitors, believe it or not. And it had some on-chip memory, not much. Best we could do, 4K. We have 32-bit memory interface, first 32-bit memory interface. It had a strong sense of time. With parallel processing, you really need to know about time. You need to know how long it's taking to run your particular bit of program because you're going to have to do lots of optimization. It's also good for applications. And it did clever things with its clocks and with the technology, and generally was highly innovative in all sorts of ways. Right. It worked with this model of communicating sequential processes, or programming language. There were multiple processes to a process. We had serial communication. We were trying to be able to maximize the communication performance. And they went fast at the time as well, 20 megabits, beg your pardon. And built-in process synchronization. So there's a lot of guff in the processor to support the concept of parallel processors. Well, what was important about the transputer? Well, of course it's British, yeah. The hardware modeled the software. What does that mean? Well, it means you can write a program and then distribute it onto a set of processors without changing the program. And that's of crucial importance. And you need it in cannot get the allocation of processes right. And you need to be able to move them around. And you probably need to be able to move them around dynamically while the program is running. And the other important thing is that we had a mathematical model. We proved our computer was correct. We proved programs could run that. And we're dealing with extremely complex situations. It's incredibly easy to write programs that don't work. When they're sequential, and you bet you've got a whole new dimension of error when you go parallel. Right, so provably correct. And I recommend that any time. So I said, what was important? It is important. It's important to everybody. And it is important to the future. So learn those lessons. Well, what went wrong with the Transputer? A lot of people say it was me. I deny that. The answer was money. And what was the second thing that went wrong? Money. The third thing that went wrong? Money. You won't believe this, but in 1984, Inmos had the fastest microprocessor in the world, apart from being innovative in all sorts of ways, and we own 65% of the most valuable memory product in the world, static RAM, and we had patents on all the memory chips, which are still the memory interfaces that we use. And we were in an incredibly good place. Now, our business plan, written in 1979, while I was playing Monopoly at Christmas, believe it or not, said that in 1984 we were going to go out to the market and we were going to raise a large round of secondary funding to capitalise on where we were going to be at that time. And we were where we said we would be at that time, but we were unable to raise money. And there's all sorts of reasons for that, but that is the situation. So Inmos got to that position and it didn't have the money to go to the next step. So that's another important lesson to learn. Money is the most important thing. And we were too clever by half. We did all sorts of things which were really, really good. Many of them still haven't been properly implemented in microprocessors or in programming techniques. But it did mean that very few people could understand what the hell we were doing. And the last thing that went wrong was the serial link. Sorry, Paul. What I wanted when we started was that we had a message passing system, so we could route information around a set of microprocessors. What happened was that the communication link used too much silicon. We couldn't afford to put in the sort of links that gave us generality. It meant that we were limited in sending a message from one transputer to one of 4 others, and it had to go in, it had to run through a program before it could get to the next, which meant that communication across a set of microprocessors was far too slow. And it wasn't until another 5 years later that we actually managed to produce a bit of silicon, which got around that problem to a reasonable extent. So, crossbar switch. Right, just a word about the chip itself. There, pretty picture. First bit of structured design that anybody had ever seen in a microprocessor. If you saw an Intel chip at that time, it certainly didn't look like this. We got on board some memory, microprocessor itself, and there you are. That's one of the 4 serial channels, and they were just too big. And an awful lot of the chip is used up around the edge. Nobody ever thinks about that because it's around the edge. But it's bigger than the microprocessor and it's bigger than the static RAM. Now we can do some useful metrics from this because basically the ratios haven't changed. The size of the basic transistors come down, but it still looks pretty much the same way. So if you look at the silicon, processing is free. You want to get as much processing local as you can. It doesn't cost anything. Memory is pretty cheap. We can actually get memory, the ratio of memory to processor is probably better now than it was then. We've been able to be a bit more clever with the memory. And then we got this problem. The expensive bit is communication. Except for trying to get on and off the chip. That's prohibitive. Yes, costs. Now the obvious thing is you want to get as much on the chip as you can. But it isn't much good in getting as much as you want on the chip by just making a more complicated processor. Now if you look at power, slightly different. Memories are good on power, and still are. Processing is expensive. You've got all these transistors that are pretty much flipping on and off all the time. So, although processing is cheap in the sense you can build a processor and it's very small in relationship to the memory system, it's actually going to use quite a lot of power. So there is quite an interesting trade-off in terms of those two. Communications, bang. Power again, expensive. And then of course, going off chip, don't. And if we look at the performance, well, the reason the transputer was fast is because you put some memory on the chip. And you could run really high performance things. As soon as you go off chip, bingo. So you've got to get all your memory on the chip. And sending communications is good on the chip. And that just says the other things. Go off chip and everything falls to bits. Where are we going to go with chips? Wish I knew. Clearly, you see the memory as a module and the processor as a module. And there's a trade-off between these two. And it's not obvious how much memory and how much processing to put on the chip. And fairly obvious what will happen is that I think people will produce different solutions to that problem and different trade-offs. And you'll probably be able to choose a memory dense chip or a processing dense chip and mix and match them. We've got to get rid of these dinosaur architectures. They're really a problem to us. Where are the manufacturers going to go? What's Intel going to do? It's got this architecture. It is so complicated, kludgy. They can't actually do anything with that. But Intel is actually under pressure from dear old ARM. You know, Intel's results weren't very good this quarter. Why? Because of ARM. It's just conceivable that Intel might try and do ARM down by producing a very simple processor. So they could actually get in underneath ARM. Probably not, because that's not the way that companies think. Usually when companies get to this situation, be it IBM or Kodak or Xerox, they die. The technology comes along and they don't respond and they die. There's ARM. What's ARM going to do? Well, it had this great idea. It had a better model than Inmos did for the way it did things. That's the difference. We went out to try and be a full mainstream silicon processor, They came along a few years later and they could actually just design things and get it processed. So ARM's sitting there, it's in a great position at the moment, but from the point of view of parallel processing, the ARM chip is too complicated. What are they going to do? So they're a bit stuck. They feel as though they're in a good position in relationship to Intel. So they're probably not being very innovative right now. Which leaves someone else to come along and provide the sort of processes you need to solve the problem. Who will it be? Who knows? There's an awful lot of Chinese out there. I mean, I think you might find that they see that as a way into the marketplace. ARM's, of course, is really pretty vulnerable because it doesn't process silicon. That's been a strength to it, but it's also a vulnerability. So I don't know what's going to happen, but I think we'll find some new companies coming along and producing the chips you want. And the one thing I do think we're going to get is that we're going to take our memory chips and we're going to put some processing on board. All sorts of things we can do with it. We can actually do verification. We can make memories which are clever in terms of accessibility. We can put semantic content into the memory. So this is a memory chip which is high density with some processing on board. And I'm sure we'll find those. And they are going to change things. So it's not really parallel processing. It's just putting something in front of the memory. What are we going to do in terms of programming? Well, you choose your language. I don't know. You choose your concurrency paradigm. Make it simple. Whatever you do when you design a language, put deprecation into the thing and try and cut out features that are in there at the moment. Many of the features that are in serial languages you don't need when you've got concurrent languages. So you just take a serial language and wrap concurrency around it, you've got a lot of redundancy. We need simpler languages for parallel programming. The future, the operating system. Well, it's obsolete. Been obsolete for 50 years. But it's obsolete in the sense that what's the operating system there for? It's primarily there to cope with the concurrency that you're hiding away from the programmer in the chip. When we've got concurrent programming and concurrent programming languages, you might want services, but they will be provided by modules you can compile into your system. You don't need an operating system in the form that we've had it for years. You can have something much simpler, much more efficient in terms of its interactions, and much more manageable. So operating systems will disappear at one level. But you're going to need something else, which we call an operating system. When you put parallel programs onto a machine, you will find that you need to optimize the way they work. And to do that, you've got to collect statistics about the way the programs run. You need instrumentation, you need monitoring, and you need measurement. And it's all got to be in there, and it probably fits in some software modules, which you might call an operating system. And the other thing you need to do is, while you're doing all of this, you're probably going to have to move processes around between the processors. You're not going to get it right, and probably even not right when you've got real parallel processing ever. And so they need to be able to move dynamically. So the operating system of the future is going to be performance optimizing. Applications. Well, I don't think many of the applications we've got at the moment run very well on parallel processing. I have no idea what the applications are going to be. You've got a chip, you've got a processor. The great thing is to go and play with it and do new things. And that's where the future's going to be. Oh, that says the future, there you are. The future is with you, it's with Parallella, it's with people doing new things with parallel processing. Good luck. We might even get a bit more parallel. Thank you very much.
Thank you very much, Ian. I think we've got time for a couple of questions, if you're happy. Ian?
They couldn't possibly be any.
Yes.
I'll take them in parallel.
I wonder if you would speak a little bit about the future. You were talking about dinosaur architectures. How do you see the graphics processors, NVIDIA and that?
Well, they're great, but they're designed for graphics processing. People are so desperate to do parallel processing that they've had to use graphics processing chips because it's the only things that have got lots of power processors on them. They're damned hard to use because they're designed very specifically to do graphics processing. So the answer is with the NVIDIA and things like that, they're just going to do more of the same. I suppose they could go into this market if they wanted, but not with their current designs.
Particularly the weakness in their current designs?
Well, no weakness, it's that they're designed rather specifically to cope with things like planes of images being put one over the top of another, shading and all sorts of things like that. So they've got rather a lot of very specialised hardware in there. But if you can use them, great.
Ian, I have one question, which is what you made of ARM's new 64-bit architecture, where they rather surprised people rather than just doing a let's layer some more stuff on the 32-bit architecture. They took the opportunity to actually try and simplify. Good. Yeah.
I think they could go a bit further.
Right.
I guess what also happened in the Transputer era was the risk explosion with quite deeply pipelined architectures, large register files. So getting a several times increase in performance through those architectural changes. But those architectural enhancements work against the kind of Transputer architecture which was optimized because process switching in RISC architecture is painful. So
Yep.
I think
That's
you
right.
were raising between the lines of the question of when you mentioned dinosaur architectures of whether a Transputer type, lightweight stack-orientated architecture would still be an option today.
Yes. Doesn't have to be a stack, but the essential thing is that you probably want to be able to simulate processes on a parallel process on a serial process. In that case, they've got to be lightweight. And in a transputer, you could have a process that was 10 instructions long, and the overheads were fine. And well, we'd sort of say we had a risk instruction set anyway. We just did it rather better, and we didn't use the name. Yeah.
Okay. Thank you very much indeed, Ian.
Thank you.